As we round out and finish Chapter 8, we're going to take what we know about probability distributions and take it a step further. And look at some very specific probability distributions, namely binomial distributions and normal distributions are most often used in elementary statistics courses. The first one we're going to look at is binomial distributions. A binomial distribution would be a probability distribution that was created by a binomial experiment. And a binomial experiment basically means that I have a fixed numbers of trials. There are only two outcomes for the experiment, success and failure. And sometimes you could alter that by depending on how you rephrase the question. Like if I'm dealing with a situation where, I'm picking things that have multiple colors, and I have more than two colors in there, but I could always say like, okay, what's the probability of red and not red? So anything that's not red would go into that group. So if I could pick a blue, a green, a yellow, whatever colors I have remaining, if it's not red, it's in the group of not red. So the probability of success in each trial is the same. So we're assuming that there is independence, basically, that 3 and 4 kind of go together because the trials are independent of each other. If the probability of success in each trial is not exactly the same, then they would be probably dependent in some way. And the formula you use to calculate a probability that, if you have a certain number of trials, you want to get the probability that, you have exactly one success, exactly two success, so forth and so on, is obtained by this formula here, where I do the combination where n is the number of trials, x is how many successes I'm looking to find out about, p is the probability of a success, and q is the probability of a failure. And if I know the probability of a success, a failure is just going to be 1 minus that. So if I know p, I'm going to be able to know q pretty easily. So with these pieces of information, let's look at this first example. The probability that a fuse produced by a certain manufacturing process will be defective is 1/50th. Is it correct to infer from this statement that there is at most one defective fuse in each lot of 50 produced by this process? So take a moment, consider it, and put your answer to the question, and then we'll go over it. Well, for this, I mean, saying that basically the probability of a defect is 1 out of 50. And that would be what P is. I mean, even though it's hard to equate success with being defective, if being a defect is what I'm looking for, then a success is something that meets that condition. It doesn't mean it's a successful thing in another kind of terminology. Basically that doesn't like cap the number of defects at 1. That's basically what this is saying, that I should never have more than 1. That's not entirely true. I mean, basically, on average, I would expect to see 1 defect out of 50. That doesn't mean I could have some production runs where I may have 2 defects out of 50 and others where I have none. It just means that as I do them over and over and over and over again, more times than not, I would expect to see 1 defect more times than I would expect to see any other numbers. That's basically the gist of it. So now for example 2, kind of looking at the formula, and hopefully you had a chance to look at that and maybe even look through your textbook and see some examples that they do. But for this one here, if the probability that a certain tennis player will serve an ace is 0.15, what is the probability that she will serve at least 2 aces out of 5 serves? So we're assuming that 15% of the time, she's going to serve an ace. So each time she serves, 15% chance that she's going to serve an ace. So based off of this, what is the probability that she'll serve at least 2 aces out of 5 serves? So try to see if you can figure it out, and give me an answer to the question, and then we'll go over it. So as I look at this, we have the probability of serving an ace is 0.15. That's the probability of a success, which means the A not success means that she doesn't serve an ace. I mean, that could be anything. I mean, it could be that it's returned. It could be that it's a fault. It could be that it hit the net. I mean, there's a whole bunch of different things. Whereas an ace is basically she serves it and the player on the other side isn't even able to touch it. Um, so the probability of success is 0.15. The probability of a failure, or Q, is 0.85, which is just 1 minus 0.15. So that means what I would have to do with this information is technically find the probability that she could serve 2 aces, 3 aces, 4 aces, and 5 aces and add them together. That would be one way of handling it. So that'd be 4 probabilities I had to use that formula for that was on the previous slide to calculate. However, it's a little easier if I think of it the fact that the probability of having 2 or more aces is 1 minus the probability of having 1 or less, because that's the exact opposite. So if I do 1 minus that, then there's only 2 probabilities I have to figure out, because I like to do the probability of serving no aces and the probability that there's no aces out of 5, or the probability that there's 1 ace out of 5, and do 1 minus that. So there's only 2 probabilities I have to figure out, whereas the other route I had to figure out and do the formula to figure out 4 different probabilities before I add those together. So a little shorter this route, not necessarily majorly short, but in some situations you may have more than an n value that's much bigger, and obviously the shorter method will certainly save you time and effort, certainly. So the probability of 0 aces is going to be the combination of n being 5 and x being 0 times 0.15 to the 0 power times 0.85 to the 5th power. And the probability of 1 ace out of 5 would be the combination with n being 5 and x being 1 times 0.15 to the 1st power times 0.85 to the 4th power. And when I carry out that computation, I get 1 minus 0.83521, which is about equal to 0.1648. And we typically round a lot of these to 4 decimal places. And you'll see why momentarily, because there's a table you use for normal distributions that only goes to 4 decimal places, and that's the main reason. So, mean, variance, standard deviation of a random variable. So if I have a situation where I have a binomial distribution, and I want to figure out the mean, the variance, standard deviation. It's a pretty simple calculations for these instances, because the mean or expected value is just n times p. We actually did an example of that in one of the homework problems we kind of reviewed already, where since it was a binomial distribution, I could look at it as being n times the probability of success. That's the expected value. The variance is just n times p times q, and of course the standard deviation is going to be the square root of that. So let's consider the following example. So the McCormick Company manufactures solar panels. As a part of its quality control, the company checks the day's production by examining sample sizes of 10. The following table shows the number of defective panels contained in a distribution of 40 samples. So there's 40 samples, each having 10 panels in them. And basically what this table is saying is that there was 33 that had no defects, 3 that had 1 defect, 2 that had 2 defects, 1 that had 3 defects, 1 that had 4, and 0 that had 5 or more. Now, the reason why that last part is in here is that it lets you know that there are no other outcomes, even though if you actually total these all up, you would see that they do total to be 40, which should have given you that idea anyway. So this is not going to be part of the probability distribution in the long run. And I'm not asked to really find the probability distribution per se, because I really kind of have it already. I mean, I could just do each one of these over 40. We're looking for the mean number of defects, and we're looking for the percentage of defective solar panels in a day's production. So essentially, this is asking us to find the value of p, written as a percentage, though. As I go through this, you're going to see I do calculate the standard deviation and the variance, but they're really not needed for this. I just wanted to make sure I got a chance to use this exercise to assist with some of those other things and to show how to do that. But this is kind of working a little bit backwards, because we're not really given we know at n is 40, we're not given what the value of p is, and a lot of problems that you're going to be given is, that's what you're going to be looking for. Um, but I can find the expected value because I have, how many samples, had no defects, how many had one defect, so forth and so on. So as I set this up, my expected value is going to be 0 times 33 over 40, plus 1 times 3 over 40, plus 2 times 2 over 40, plus 3 times 1 over 40, plus 4 times 1 over 40. So when I add those together, multiply those up and add those together, I get about 0.35, and that's what the mean is. So on average, I expect 0.35 on average defects for each sample. So that means probably more times than not I'm going to have none, but one is not very atypical either. Now as I go through this now, I also keep in mind that the mean is n times p, and I already know that n is 40. So to figure out what p is, I'm just going to take 0.35 and divide it by n, which is 40. And that gives me 0.00875. So that's the probability of a success, which means Q would be a 0.99125. Now, if I wanted to calculate the variance and the standard deviation, of course, the variance would be 40 times P times Q, which would give me about 0.349375. And square rooting that, I'd get about 0.5890 for the standard deviation. Now, we weren't asked to find those things, but I just wanted to kind of use this example to show that anyway. We found what the mean was. That's the 0.35. We found what P was, but the only thing we have to do is to put it as a percentage, the percentage of defects in the day's production would be given us by, me turning that 0.00875 to a percentage, which would be 0.875%. So that's the percentage of defects I would expect to have in a day's production of that. So moving to the next question. As a part of its quality control program, the video cartridges produced by Star Communications are submitted to a final inspection before shipment. A sample of 6 cartridges is selected at random from each lot of cartridges produced, and a lot is rejected if the sample contains one or more defective cartridges. If 1.5% of the cartridges produced by Star is defective, find the probability that a shipment will be accepted. So, take a moment, see if you can come up with a probability for this, and then we will go over it. So for this, the information that we were given from the beginning is that, well, first of all, the probability of being accepted means that it's a probability of having no defects. If it has one or more defects, it's rejected. So, and this is out of six cartridges. So basically, N is going to be 6. P is 0.015 because that's 1.5% written as a decimal. Q, of course, would be 1 minus that, which would be 0.985. So the probability of being accepted would be the combination of 6, 0, where n is 6, and of course x is the number of defects, which is none, times 0.015 to the 0 power times 0.985 to the 6th power. And if I calculate that out, I get about 0.9133, which means there's about a 91% chance that the shipment will be accepted and shipped out. It's not going to be rejected and prevented from going out to the public. So now we'll look at some normal distributions. Normal distributions are most often the types of distributions that are used in statistical analysis. And if you do have to take any kind of statistics course in your future, you're certainly going to see normal distributions a great deal. So, but the probability distributions, up to this point, they take on finite many values. So these are going to deal with continuous probability. So basically, a binomial distribution it deals with discrete data. So it's often if we're counting things. A normal distribution is a type of continuous probability distribution, and that is typically something that we use if we're measuring things. Like if I'm looking at distances or heights of things, or anything else that tends to be even test scores, which are kind of, because tests are considered to be measurement tools. Those are considered to be measurements as well, so they're continuous statistics. So when we use a normal distribution, the probability is non-negative for all values of x, which is like the same as it was before. The area of the region between the graph of a distribution and the x-axis is equal to 1. So essentially what we're going to be doing is, using methods that help us find the area underneath what we call eventually a normal curve. And that area should be total to 1 on average. So when I ask to find the probability of an event between two values, I'm looking to find, the area underneath the curve between those two values. That gets into some, like, how these things are come up with. That requires some calculus to be talked about, and you're not going to be required to know anything behind that. You're going to be using the tool, not developing it. So for normal distributions in general, the normal curve, if it is a perfectly normal distribution, the mean is in the middle, because the mean should be the same as the median, and it should be the same as the mode. So the most frequent score should be the same as the average score, which should be the same as the middle score. And basically, the way the distribution tends to work is that 68.27% of scores or values lie between one standard deviation away from the mean. So one less than or one more than. 2 standard deviations away from the mean, you should have about 95.45%. And if you have 3 standard deviations away, between those, you should have 99.73% of the entire sample or population in between those parameters. So we don't often use these as the sole means of calculation. I'm going to show you how to use a table momentarily to kind of do some of this information. But let's continue on with some more information about this. So the curve, for a normal distribution has a peak at the mean. The curve is symmetric with respect to the vertical line, x equals mu, which is the mean number. And we're going to make use of that as we use the table at times, because sometimes, you might do a little calculation. Other times, if you handle it correctly, you just have to look at, something else on the table, which you should know should be equal to what you're looking for. The curve always lies above the x-axis, but approaches the x-axis as x extends indefinitely in either direction. So basically, this will continue on, and this curve will continue on and get infinitely close to the x-axis, but never cross through it. The area under the curve totals 1, just like we talked about in the previous slide. And for any normal curve, and it's talking about the percentages here, and I've already talked about those. Now, the table I'm referring to, it's also in the packet. It's also in your textbook. This is the table. It has 2 parts to it. It's on 2 different pages. One deals with the negative z-scores, and the other one deals with the positive z-scores. We'll talk about how to use these momentarily. But this is based off of a standard normal distribution. A standard normal distribution is one that has a mean of 0 and a standard deviation of 1. So when we start dealing with circumstances, because most things that you're going to be studying will not have that. They're going to have a mean of some number, a standard deviation of some other number, and they're not going to be 0 and 1 respectively most of the time. If not, it's very rare if they are. So what we end up doing is converting it into a z-score so we can use this table. And notice the table has 4 decimal places. Now, for like the final exam, you will be given this table if necessary for probabilities. Calculators know the TI-83s know how to work these out, but a part of this course is not to go through that. So you're more than welcome to look it up and see if you can manage to do that. But let's see how we can make use of this table, the idea of a normal distribution, to answer some questions. So the first question is kind of basic here. Find the value of the probability of the standard normal variable z corresponding to the shaded area under the standard normal curve. So the first one here is that you're looking for the probability that z is less than 1.45. So see if you can read the table and come up with the right value, and then I'll demonstrate. So to do this, I'm looking for a score that's less than 1.45. So if I go to the table, I want to be on the positive table where the positive z-scores are. Now, keep in mind as I do this, so let's go back to this table here. It's always an area that's to the left of z. So these are always going to give me areas to the left of a value. So, I'm having the right region, so all I have to do is find 1.45 on this table. And so if I come down to this formula here, 1.45, I'm going to come to the 1.4 column, or row here. This is 1.40, 1.41, 1.42, 1.43, 1.44, 1.45. So this is the value I'm going to use as my probability. So the probability that z is less than 1.45, going back to the slide now, is going to be that 0.9625 I found on the table. So that's pretty straightforward. The next one. It's still an area to the left, so this one's pretty easy as well. I just got to look up negative 1.75 on the table. So going back to the table, I'm going to go to negative. I'm going to look up negative 1.75. So I'm going to go to the row negative 1.7. This is negative 1.70, 1.71, 1.72, 1.73, 1.74, 1.75. So this is the value I'm looking for. So 0.0401, so the probability that z is less than negative 1.75 is 0.0401. And for some reason, when I transfer this over to the PDF file, the negative sign doesn't appear on the picture, but keep in mind it's supposed to be there. You're not always going to be given things that have areas to the left. Sometimes you might have an area to the right. Sometimes you may have an area between two values, like this one. The probability that z is between negative 1.32 and negative, or in between negative 1.32 and 1.74. So try to see if you can figure out a way of figuring this out. If you want to consider this, basically in this circumstance, I can think of this as, okay, well, I have two circumstances here. I can find the probability of being less than 1.74, which I do expect to be, bigger, and the probability negative 1.32, because remember, in a standard normal distribution, this is 0. This is basically the area to the left of 1.74 minus the area to the left of negative 1.32. So it's basically me subtracting these two areas from each other. That would give me the area here. So the first thing I do is I make note of that. The probability that this is equal to the probability of z being less than 1.74 minus the probability of z being less than negative 1.32. And I look up those two values on the table. So going back to the table, a positive 1.74 is on the second page. Let me get a different color here maybe. 1.74 would be 0, 1, 2, 3, 4, so 0.9591. and less than negative 1.32, so I need to look up negative 1.32, negative 1.32, negative 1.3012 is right here. So I have 0.9591 minus 0.0934. And that's what I subtract, which gives me a probability of 0.8657. Now, as again, you're not going to often be given circumstances where you just say, hey, here's the z-score, find the probability of this. You're often going to have to calculate the z-score given certain data. And the way that you calculate a z-score is by taking whatever piece of data you're looking at, and we'll talk. And so, if I'm saying that x is like less than 100, well, the score I'm looking at is 100. I subtract away the mean, and I divide by the standard deviation. That gives me a z-score. So, for instance, looking at this example here, suppose x is a normal random variable with the mean being 50 and the standard deviation being 5. Find the probability, or find the value of the following. So the first one is the probability that x is less than 60. So the first thing you're going to need to do is change this into a z distribution. You want to say, okay, well, if the score is 60, what's that for a z-score? Which means that z would have to be less than a certain amount, and go from there. So use that idea and see if you can come up with the probability for A. Well, for A, the probability that x is less than 60 is going to be calculated from me doing 60 minus 50 over 5. So z is going to be less than whatever that equals, and that happens to equal 2. So I'm looking for the probability that z is less than 2. So when I come back to here, and I'm going to go to the positive z table, I'm looking for the probability of being less than 2, 2.00, so that's 9.7 or 0.9772. And that's what the probability is. So the probability of being less than 2 is 0.9772. Now try the same thing with the probability of x being greater than 43. This one's a little bit trickier, because notice it's a greater than this time, not a less than. How are you going to handle that? Well, there's two ways you could actually handle this circumstance. But the first thing I'm going to do is translate this into a z-score situation. So I'm actually looking for the probability that z is greater than 43 minus 50 over 5, which means that z is greater than negative 1.4. Now, one thing I could do is say, okay, well, first, I'm looking for the probability essentially in this circumstance, and I'm going to draw it in the banner up there. In this situation, I'm looking for the probability. Here's negative 1.4. I'm looking for this area on this side. Now, one way of handling this is say, okay, well, if I just find the probability, this probability in here, and do 1 minus that, that should give me the area that's over in that side. So that's the first way I kind of showed it. So I do 1 minus the probability that z is less than negative 1.4. And so I go to the table. I want to go to the negative table, so I want to go to the first one. I'll just change it to see another color. Negative 1.4 is right here. 0.0808. So my probability is going to be 1 minus 0.0808, which is going to be 0.9192. The other thing I could keep aware of is that, well, the table does give me a circumstance where I have 1.4 on this side, and I get this entire area. The table will actually give me this. And I have to realize that should be the same as this area over here because of the symmetry of this thing. So, being less than 1.4 should be the same as being greater than negative 1.4. So, if I thought of this as being the probability of z being less than 1.4. And again, using the table, instead I would go to the second table and say, okay, 1.4, and I'm looking for less than that. You can see that the 0.9192 is the answer that's there. So there's different ways to approach this based off of how you interpret the table. So you have to make sure that you are interpreting the table carefully. So for C, give C a try, and then we'll go over it. Well, since I'm running out of some room over here, let's move to the left for this one. So I'm looking for a circumstance where, one score is below the mean, the other one's above the mean. So if I knew if it was a different location, how I would handle it is differently, but this is really no different than I would handle it before. I'm going to do the probability of x being less than 58 minus the probability of being less than 46. It's the less than 46 is this part right here. So if I lop that part off, that's going to give me the probability between these two values. But again, I can't use the table to figure it's not based on the x's, so I got to convert these to z-scores. So this is actually the probability of z being less than whatever 58 minus 50 over 5 is, minus the probability of z being less than whatever 46 minus 50 over 5 is. And that gives me the probability of z being less than 1.6 minus the probability of z being less than negative 0.8. And when I look these values up on the table, I get 0.9452 for the probability of being less than 1.6. And I get 0.2119 for the probability that z is less than negative 0.8. And of course, when I carry through that subtraction, I get 0.7333. For the last part of this, 8.6 is just applying what you know about normal distributions. And in actuality, if you have a binomial distribution that's big enough, you could also use normal approximation on it. And we'll kind of talk about that too. So, example 1, TKK Products manufactures electric light bulbs in the 50, 60, 75, and 100 watt range. Laboratory tests show that the lives of these light bulbs are normally distributed with a mean of 750 hours and a standard deviation of 75 hours. What is the probability that a TKK light bulb selected at random will burn more than 900 hours, less than 600 hours, between 750 and 900 hours, and between 600 and 800 hours? So take a moment to figure out what these 4 pieces of information are. Make sure you give a probability with 4 decimal places, and then we will go over it. Okay, so as I start this off, I have to use the fact that they did give us the mean and the standard deviation as 750 and 75 respectively. Now, these are all x values. I'm looking for more than x being 900, more than or less than x being 600, so forth and so on. I have to be aware that, again, the table gives me a lot, are good for the less thans. The more thans, I have to make sure I'm using symmetry or doing 1 minus the probability of something else, depending on the circumstance. So for the first one, the probability of a randomly selected light bulb lasting more than 900 hours is basically the same as the probability that z is greater than 900 minus 750 over 75, which of course would be 2. Now, using symmetry again, we're looking essentially, for this area here, where z is 2. Meanwhile, if we look at the right spot of the table at negative 2, I'll have this area. These areas should be the same thing. So that's what I'm noticing here because of the symmetry. Being more than 2 should be the same area as having z less than negative 2. So I would go to the table now and look up a z-score of negative 2, which I've done before. It's 0.9772. And so the probability of this is or less than -2, I should say. I went to the wrong one. Give me a second. Yeah, I went to +2. I should be going to -2. So -2 would be 0.0228, and so that is the probability that I have for that. For lasting less than 600 hours, well, again, I'm looking for this. So I'm going to convert it to a z-score, which means I get the probability of z is less than -2, which is kind of ironic because, I already calculated that, so I expect it to be as well as 0.0228. Between 750 and 900 hours, again, you always want to kind of get an idea of what's going on here. 750 happens to be, the mean. So when I look at the circumstance between the mean and 900, okay, well, I know that this portion right here is 0.5 because, at the mean, I should be at the 50% point. So 50% should be above, 50% should be below. What I'm looking for is, if I do the probability of being less than 900, I would get this area all the way from here all the way down. But if I take off the 50%, essentially, that goes to the left of 750, that's going to give me the probability I'm looking for. So that's what I mean by sometimes planning it out. Sometimes this picture does help of knowing what's going on. Since the mean is involved, I can just say, okay, well, in this instance here, I'll find the probability that x is less than 900, and then subtract away 0.5 from it. Of course, we've already dealt with the circumstance where x is less than 900. Z would be less than 2 in that instance. Now it's subtract away 0.5. And being less than 2 gets me back to the table, and I'll go to the positive one now and look up 2, and that's where the 0.9772 comes into play. So when I carry this through, I'm going to have 0.9772 minus 0.5, which is 0.4772. Between 600 and 800 hours. Now here's an instance again. Someone's kind of getting off the screen here. But 750 is in between those two. So when I want to do the probability of that, I'm going to do the probability of being less than 800 minus the probability of less than 600, and that should give me what's left in between these two. So that's my strategy. The probability that x is less than 800 is the same as the probability that z is less than 0.67. And the probability that x is less than 600 is the probability is something I've already come up with before, because that was part B. That's the 0.0228. That's why you don't see me doing much of a calculation there. And so I look up the 0.67, and I get 0.7486 minus 0.0228, which is about 0.7258. Example 2, the scores of an economics examination are normally distributed with a mean of 72 and a standard deviation of 16. If the instructor assigns a grade of A to 10% of the class, what is the lowest score a student may have and still obtain an A? So try to see if you can figure this out. Go to the nearest percentile and be careful about that, because we're going to have to talk about that momentarily as to why. And then we'll talk about it more. So this one's a little different because here they're essentially giving us the probability that we would need to calculate, and they're asking us to find the score, the x value, ultimately. So basically I'm going to work my way backwards from a probability to a z-score, and then from the z-score to a score. So I'm still going to use the fact that the mean was 72 and the standard deviation was 16. I'm going to be looking at a normal distribution, and I want 10% of the scores to be A. So anything in this region to the right of this score here, whatever it is going to be my A's. Which means that, and I'm doing this because the table always deals with areas to the left, that means that 90% I expect to be below this score. So I'm actually looking for the fact that the probability that z is less than some value a, which gives me about 0.9. Now this one's a little bit more tricky because I got to try to figure out what this a value is. I got to figure this particular z-score. That's what A is going to be. Um, so I got to kind of work my way backwards on the table. And since I know it's going to be above the average, I'm going to look in the positive table side. And so, whichever is where I am right now. And what I'm looking for is to find a score that is closest to 0.9. So if I look down here, that's 0.9032, a little big. This is closer, 0.9015, still a bit over. This is a bit under at 0.8997. This is 0.003 under. This is 0.15 over. This one here, the 0.8997, is the closest to 0.9. If I can find it exactly, great, but sometimes you're not going to be able to. So when I look at the score here, this is 1.28. So the z-score that has an area to the left of about 0.9 is 1.28. So I make note of that. It's about 1.28. And that's my z-score. That's my particular z-score here. So if I was doing a z-distribution down here, this would be 0, of course, and this would be 1.28 approximately. So I'm going to calculate the score minus the mean over the standard deviation should be about 1.28. So I multiply both sides by 16 and then add 72. I get 92.48. So right here is 92.48%, or whatever the score of 100 is. I want to make sure that I have that score, to make sure the lowest score, to make sure I have an A. So I want to be over that. So it'd probably be best for me to say I have a 93% to put me definitely in that range. So I would like to say that to have an A, a 93% score or more is needed for this circumstance. Now for the next example we're going to look at a circumstance where we are going to approximate a binomial distribution by using a normal distribution. We've already talked about the fact that the mean of a binomial distribution is calculated by doing n times p, and the standard deviation is calculated by doing the square root of n times p times q. You can use that as the mean of standard deviation for a binomial distribution to approximate the probability rather than calculate each of the probabilities using the formula we used earlier in this video to do it, because those calculations could be somewhat daunting. The problem is, though, obviously you're taking a normal distribution, which is for a continuous distribution of continuous data, to approximate a binomial distribution, which is supposed to be discrete data. So there's some issues along with that. So there's some conditions under which you can use this. And what that means is, the way they state it here is that if n is large and p is not close to 0 or 1, they're kind of vague on this. But typically in a lot of statistics books, the condition under which you can use a normal distribution to approximate a binomial distribution without losing a whole lot of accuracy is that both n times p and n times q have to be greater than 5. If you find out that's not the case, then you're going to more than likely have to do the binomial distribution to come up with anything accurate. If you try to use a normal distribution to approximate it, it's going to be quite a bit off typically. So let's see how we can make use of this, though. So a marksman's chance of hitting a target with each of his shots is 60%. If he fires 80 shots, what is the probability of his hitting the target at least 30 times, fewer than 25 times, and between 15 and 45 times inclusive? So take a moment, answer these 3 questions. Again, about 4 decimal places, and then we'll go over it. Well, as you can see here, I mean, one of the reasons why you may want to do normal approximation is because if I'm looking for the probability that he's hit the target at least 30 times, then I have to do the probability of 30, 31, 32, 33, all the way up to 80, which would be a lot of probabilities to calculate using that binomial formula. Or I could do 1 minus the probability of 0 through 29, which again is not much better. That would still be 30 calculations I had to do to get the probability that I need to answer this question. So using a normal approximation or using a normal distribution to approximate this is certainly going to streamline things a bit. And so if I look at this really carefully, right now, the probability of success is 0.6. 0.6 times 80 is 48. So n times p, which that's my mean, is 48. That's well over 5. And if I look at nq, which would be 0.4 times 80, I would end up with getting like 32. That's well over 5 as well. So this is sufficiently big enough for me to use the normal distribution to approximate this, which makes things a lot easier because I'm going to calculate the mean and standard deviation. Well, n times p I kind of already figured out was 48. The standard deviation, I do 80 times 0.6 times 0.4 and square root that, so I end up with the square root of 19.2. And I'm going to keep it like that for the time being because, it's not really a nice number to deal with. It's irrational, and I'd have to round it, and I try to avoid rounding as much as I can. So we'll find the probability that he hits the target at least 30 times. So I'm looking for the probability that x is greater than or equal to 30, which would be 1 minus the probability of x is less than 30. Again, I'm going to a less than mostly because of the fact that I know that the table primarily deals with, less thans. I could also just kept it the way it is and then gone with that. But again, I'm kind of handling the equal to part nicely here because, I want to make sure that, that this is the exact opposite without the equal to. So the probability of x is less than 30 would be the probability that z is less than negative 4.11. Now, if you look at the table does not go up down this low for a negative 4. I mean, so they basically usually tell you to assume 0.0001 for this, but it's actually beneath that. So if so I'm going to say the probability is about 0.9999. And, since, it makes sense because I expect to hit it 48 times. So, I mean, it's almost certain that I'm going to hit it at least 30. Of course, it'd be a rare occasion if it didn't. So, if you want to say it's more than that, if you want to say it's approximately 1, that's also okay, too. But basically, it's almost certain that this marksman is going to hit it 30 times or more. Fewer than 25 times, again, I'm going to do the probability that x is less than 25, which basically is the probability that z is less than negative 5.25. And again, it doesn't go down that low. So, I know it's going to be less than 0.0001. So that's about nothing. So there's basically no chance that this marksman is going to hit fewer than 25 times on average. Okay. Between 15 and 45 times inclusive. For these kind of distributions, there's a way of handling that in the realm of statistics. We're not going to get into that so much in this one. But between 15 and 45 times would be the probability that, x is less than 45 and p is minus the probability that x is less than 15. The equal to parts with this many numbers doesn't really matter that much. It's a very insignificant difference. So, and again, the probability that x is less than 15 is that z is less than negative 7.53. So this is basically 0. I could probably say, okay, this is nothing. I'm gonna look for the probability that z is less than negative 0.68. So I looked that up on the table. I get about 0.2483, of course, minus 0. So about 0.2483 is the probability of the marksman hitting between 15 and 45 times. We expect them to hit it more than that. So, And that is the end of this. So if you have any further questions, please make sure to bring them up in class. Until then, have a good day.